Let me just give a brief introduction of very learned person, Dr. Pramod Ji. He is currently working as associate professor at the Manipal University of Technology, MIT, Bangalore, BP, associate professor. He has done his BE in mechanical engineering in 2002 from Central University, Maharashtra. He is completed MTech in thermal and fluid engineering in July 2005 from Dr. Babasaheb Ambedkar Technology University, Lolere, Maharashtra. And he has done his PhD in propulsion Department of Aerospace Engineering in September 2010 from Indian Institute of Technology, that is IIT Bombay. As I said, he's currently working with MIT. He has having his main research interest in the performance improvement strategies for turbo machines, flow control of internal and external flows, thermal energy storage for different applications. He also has done a lot of research and he holds some patents in his name. That is for the solar space heating system, which application is filed in 2018. Also active flow control of axial flow compressors using synthetic jet actuators. This patent application is filed in June 2021. And the third patent which he has filed is for the system for thermal management of a lithium-ion battery. That is in the year April 2022. And he's been giving the lectures, publishing articles in very national as well as international magazines, and conducting seminars and attending conferences in India as well as abroad. His biodata is quite in much detail. We don't have that much time to go through. He has been awarded and received some recognitions. That is Award for Excellence in PhD thesis work from IIT Mumbai on 5th August 2011. And this award was chosen amongst the aerospace, mechanical and energy systems and engineering departments. He has also received trial grants from Department of Science and Technology to present a paper at 3rd European Conference for Aerospace Sciences held during 6 to 9 July 2009 at Paris, France. Again, a trial grant from Indian Institute of Technology in Bombay for presentation of paper at 9th International Gas Turbine Congress held in December 2007 at Tokyo, Japan. Secured a second university rank in the MTech program at Dr. Babasaheb Ambedkar Technological University, Lolere in the year 2003-2005. And a reviewer of renewable and sustainable energy reviews, experimental thermal and fluid sciences, ASME Journal of Fluids Engineering, Applied Thermal Engineering, Journal of Applied Fluid Mechanics journals. So this is such a vast biodata and credentials he's having at such a young age. He's just, I think, 42 years. And Dr. Pramod, we are very much eager to listen to you.
The topic of my today's presentation is insights on flow control techniques in aerospace applications. In this presentation, we will see the basic phenomena, that is flow separation, then what is flow control. There are different flow control methods that we'll see, the active and passive flow control methods. And then we'll see the applications of these flow control methods in two different applications. One is axial flow compressor and second one is unmanned aerial vehicles. Axial flow compressors, I did a research during my PhD days, and also currently also I am pursuing the research on the same. And the other application, that is unmanned aerial vehicles, that I did one postdoctoral fellowship at Nanyang Technological University, Singapore. So there during 2012 to 14 I worked on that. So that also I will cover. And then at the end we will see the practical implementations of flow control techniques and the difficulties in their industrial adoption. So first we'll see the flow separation. Flow separation is nothing but the separation of the boundary layer flow from the surface. So when there is a adverse pressure gradient in the sense when the flow takes place and when it opposes, when it experiences the flow in the increasing pressure, such as the aerofoil which is set at higher angle of attack. So in that case, the trailing edge of the aerofoil, it experiences the flow moving in that region experiences the positive pressure gradient, and that we say as adverse pressure gradient. So in such situation, what happens? The boundary layer flow has already lower momentum because the flow velocity varies from 0 to 99% within the boundary layer region, and when it experiences the higher pressure gradient or positive pressure gradient, the the boundary layer flow do not have enough momentum to move further. So at a particular situation, what happens? The boundary layer flow comes to rest and then it reverses its direction. So it separates from the flow, from the surface, and we say that the flow has been separated. And other term for this flow separation is the stall insertion. That is, the aerofoil has been stalled or the blade has been stalled. So that is basically because of the adverse pressure gradient. Now, the flow may separate either from the blade surface or from the wall surface. So here in the figure, we can see the flow separation. The top figure, it shows the flow separation from the wall, and the bottom figure, it shows the flow separation from the blade. Hatched region, it shows the separated flow. Now, the flow separation is not at all desirable because it has various deteriorating effects. The first and major effect is it increases the drag significantly. Therefore, there must be some mechanism where we can control the separation of this flow. So we will now see the what is flow control. So flow control is not like we daily come across the control of the flow using a tap. But this flow control is the one where we modify the boundary layer flow and improve its performance so that the flow is not separated from the either wall or from the blade surface. And the necessity of the control of the flow is to delay or eliminate. Elimination in most of the cases may be difficult, but delay of the flow separation is obviously possible. So the delay or elimination of the flow separation and to improve the stall margin. So the stall margin is related to the axial flow compressors. The second necessity is to enhance the pressure rise across the compressor, because the function of compressor is to increase the pressure ratio. And third one is to reduce the fuel consumption. So once we increase the stall margin and increase the pressure rise, the amount of fuel required automatically goes down. So these are the important necessities in an axial flow compressor, which shows the importance of the flow control. There are two broad methods of flow control. One is passive flow control method and second is active flow control method. In passive flow control method, it is basically the geometric modifications of the casing, such as the slots and grooves that we'll see in the subsequent slides. The important advantage of passive flow control method is we do not require any external energy. So the zero energy requirement is there. But the disadvantage is, since we do not have any control, once we start the machine or start the engine, we do not have any control on the passive flow control device. So it cannot be turned off whenever we want. And when we install the passive flow control device, it adds up the frictional losses. So though there are some advantages, some disadvantages are also there, such as increase in the turbulence and increase in the losses. So the increase in losses brings down the compressor efficiency down. The second method is active flow control method, wherein the external energy is required to cause the control. Okay. The important advantage of the active flow control method is, as per the requirement, the active flow control method can be switched on or switched off. Now we'll see different passive flow control methods pertaining to the axial flow compressors. This includes the circumferential grooves, then axial slots, skewed slots, bent slots, honeycomb casing. These are different, some of the passive flow control methods. So in figure 3, you can see there are some grooves are here. So these grooves are made on the internal casing surface of the axial flow compressor testing. And whenever the flow passes through these grooves, it actually generates the vortices. And these vortices, when they come out of the groove, they interact with the low energy flow and give their energy. So because of this momentum exchange, the flow separation is delayed or eliminated. These are other configurations of passive flow control, such as the honeycomb casing, then again circumferential groove, then axial slots and skewed axial slots that we can see. So different geometries can be made and the performance can be tested. This is for the axial slots. So in figure 5, you can see the left side, it shows the cut section, and it shows different kinds of rectangular slots. These slots are fabricated on the inside surface of the casing. Where the flow comes, it enters the slot and generates the vortices. The front view you can see here on the right side figure, wherein the cavity, rectangular shaped cavity is seen. So that cavity is intentionally provided so that the flow passes through the slot and it churns and creates the turbulence. The skewed slots, it is observed that they provide the higher stall margin as compared to the non-skewed slots. And it is also observed that if we provide if we increase the depth of the slot, okay, depth is the thickness of the slot or the height of the slot. If we increase the higher height, then it gives more performance because it gives more churning within the slot and the momentum exchange from this flow which is passing out through such slot, it gives higher performance. Now we'll see active flow control method. As I told you earlier, it requires the external energy addition. So here we will see different techniques through which the active flow control method can be accomplished. The first one and the basic one is the air jet injection. It is also called as the tip injection. So in case of tip injection, we basically inject the compressor air before the leading edge of the rotor. Okay. So the tip section means where the span is around 100%. So that tip section of the compressor rotor is very critical and it is the region which is prone to the flow separation, where the momentum of the flow is lesser. So there the stall inception occurs at the tip. If we supply the high momentum air at the tip region, then it affects significantly in damping out the stall precursors or stall disturbances. So the first one is the air jet injection, then the synthetic jet actuation, then plasma actuation, inlet guide vane control, suction of the low energy boundary layer flow, and suction and blowing. So these are the different methods. Out of these, the first three are current lot of research is going on these methods, and last three they are not very popularly used. In earlier days, inlet guide vane control was tested a lot, but nowadays it is stopped because inlet guide vanes, the function of these inlet guide vanes is to control the flow which is passing through the axial flow compressor and increase the incidence angle, that is the flow while enters the axial flow compressor. The reason that nowadays the inlet guide vanes has been stopped using because these inlet guide vanes increase the weight and the space, consume a lot of space of an axial flow compressor or the overall engine. So the inlet guide vanes or IGVs are now the peoples are not using. We'll see these one by one. The first one is the tip injection. As I mentioned earlier, in the figure 7, the top figure you can see here the tip injector which is near the casing, and the compressed air actually passes through this injector, and the red shaded zone, it indicates the compressed air. The rotor, you can see it here. So at the tip of the rotor, the air has been injected and it's the momentum of the retarding boundary layer flow is increased. The injection may be steady or unsteady. If it is unsteady, we call it as a pulsed injection. So it is also observed that if we give the pulsing to the injection, it is more effective because it helps to generate more vortices, and the energy exchange is significant as compared to that of continuous injection. In case of tip injection, the important factors that affect the stall margin of the axial flow compressor, they are the injected mass flow and momentum. So higher the mass flow and the higher will be the momentum. The pitch and yaw angles of the injector. So pitch angle is with respect to the vertical direction, and yaw angle is with respect to the sideways direction. Third one is the axial location of the injectors. So if we keep the injector close to the leading edge, blade leading edge, the usual distance is around 2 to 3 millimeters, then the momentum exchanged by the injected flow is significantly higher. But if we keep the injector quite away, such as 6 or 7 millimeters, so higher the distance between the blade and the injector, the momentum is lost by the time the jet reaches the blade leading edge. Therefore, it is always advised to keep the injectors close to the blade leading edge. Then circumferential distribution of injectors. So the injectors has to be placed circumferentially equally. If you use very few number of injectors, the area covered by the injector along the circumferential direction, it will be less, and therefore it may not effect significantly towards the highest possible compressor performance. And finally, the injection velocity ratio. So injection velocity ratio is the ratio of jet velocity divided by the compressor air mass flow, compressor air velocity. So it is recommended to use the velocity ratio at least 2. That means whatever the air is entering at the compressor inlet, so the jet velocity must be twice of that velocity. Only in that case the injection can help in controlling the flow separation. The next technique is the synthetic jet actuation, which is a recent technique which is used to control the flow separation. The synthetic jet actuator, it basically comprises of an piezoelectric diaphragm. So as you can see here, the left side figure of figure 8, at the bottom side there is an piezoelectric diaphragm which may vibrate upward and downward, and there is an actuator geometry, and on the opposite side of piezoelectric diaphragm there is an orifice. So this actuator is fitted wherever we want to control the flow, such as inside the wing surface, and the orifice, it is exposed to the outside air. So as you can see, when the piezoelectric diaphragm moves down, as you can see here in the animation, the outside air flows into the cavity, and the upward stroke of this piezoelectric diaphragm, it expels this fluid through the orifice. So when the fluid is forced to eject through the orifice, it forms a train of vortices, and this train of vortices, it moves upward. When it moves upward, the outside flow interacts with this train of vortices and creates the vortices, and these vortex structures further help to further interacts with the boundary layer flow and exchanges their momentum. So by this technique, the flow separation can be controlled or eliminated. Now, as I mentioned you, I will be covering here the two applications of flow control. One of them is axial flow compressors. I studied the axial flow compressors and did a research during my PhD days, and currently one PhD student is pursuing his research on axial flow compressors. The second one is unmanned aerial vehicles, which I did the research work during my postdoc at NTU Singapore. So we'll see this one by one. The first one is axial flow compressors. The broad and preliminary level of classification of turbo machines is shown here. So they are classified based on the power absorbing device and power consuming device. So the left side, it shows the power producing device, where the fluid energy is used to convert into mechanical energy, such as turbine. Turbine is a power producing device. So these turbines, again, based on the direction of flow, they are classified as axial flow turbines, radial flow turbines, and mixed flow turbines. On the right side, it is the power absorbing device, means which absorb the power. For that, they require the electricity, and using that electricity, the mechanical energy is converted into the fluid energy. So the compressors, pumps, blowers, fans, these are the examples of the power absorbing devices. And the compressors, they are further classified as axial flow compressors, radial flow compressors, and mixed flow compressors. So in axial flow compressors, the entry and exit of the flow is axial. In case of radial flow compressors, the entry and exit of the flow is radial. Whereas in mixed flow compressors, the entry of the flow may be axial and exit is radial, or vice versa. That means entry is radial and exit is axial. Now we'll in this presentation we will focus on the axial flow compressors. The axial flow compressor along with different stages is shown in figure 11, and you can see here the different components of axial flow compressors are: one is the row of rotor, second one is a row of stator, third one is casing, and fourth one is hub. So here in animation you can see the one row, there are 4 rows, and these 4 rows are rotating about the axis. So these are the rotors which rotates. They are fitted on the hub. Hub is the blue colored shaft on which the rotors and stators are fitted. Okay, and followed by the rotor, there is a stator. Stator is stationary part. The function of stator is to guide the flow towards the next rotor row at a particular angle, and also to contribute to the pressure rise. So in case of stator, the pressure rise is happening because of conversion of energy. The kinetic energy is converted into pressure energy. So here, one row of rotor and one row of stator comprises one stage of compressor. So here there are 4 stages are there. So 4 rows of rotor and 4 rows of stator. So we can say this is a 4-stage compressor. Per stage, the pressure ratio in case of axial flow compressors varies from 1.1 to 1.4. There are different applications of axial flow compressors apart from the aircraft engines. The other applications are power generating stations, then blast furnaces, air separation plants, fluid catalytic cracking, refineries, etc. Now, one question may come that why axial flow compressors are used in case of aircraft engines? Why not other such as the mixed flow or the centrifugal compressors? The reason is axial flow compressors give the smallest drag force, and second important reason is the multi-staging of axial flow compressor is very easy as compared to the centrifugal compressors. Centrifugal compressor, the frontal area is quite large and multi-staging is very difficult. So for aircraft application, they are not suitable. Also, if you see the table 1, here it gives comparison between the performance of axial flow compressor versus centrifugal compressor. The mass flow that axial flow compressor deals with is significantly high. It is more than 100 kg per second, whereas for centrifugal compressor it is very less. Axial flow compressors have higher efficiency. They can be multi-staged in more numbers, so number of stages are more. It creates more thrust. It is compact and lightweight compared to the centrifugal compressor. There are 2 disadvantages. One is the pressure ratio per stage, but this is for a single stage. When we have the multi-stage, the overall pressure ratio of axial compressor is significantly higher than centrifugal compressor. But if you use only one stage, the pressure ratio of centrifugal compressor is more. The design of axial flow compressor is very complicated and therefore it is expensive. In these slots, we have varied 3 parameters. One is the length of the slot. Length of the slot, we have kept 3 different lengths. One is completely from the leading edge to trailing edge. Second one is from 20% of leading edge to the trailing edge. And third one is 40% from the leading edge to the trailing edge. This is one. Second one is the depth of the slot, 5, 7 and 10 millimeter. These are the 3 different depths we have studied. And third one is the skew angle. So we have used 3 different skew angles, 30, 45 and 60 degree. And we have performed the simulations, and among these, the best performance is observed when there is a full slot length, that is from leading edge to trailing edge, with 10 millimeter depth and 60 degree skew angle. So you can see the stall margin is 22.6%, which gave the best performance. Here is one of the results, which shows the variation in axial flow velocity. So the ordinate is from 0 to 1. It is actually the blade span, means blade height, and along this blade height, the variation in axial flow velocity is given. As I told you, the stall basically it starts near the tip surface. So at the tip, that is at the top side, the velocity, axial velocity should be high. Unfortunately, in baseline case, that is without any control, this velocity is low. So as you can see here, the black line which shows the baseline case, means without any active or passive control, it is having small magnitude. The x-axis is normalized axial velocity, whereas when we implemented the passive flow control method, it increases significantly. So as you can see here, the D10 S60, that is depth of 10 and skew angle of 60 and leading edge to trailing edge slot, it significantly increased the axial flow velocity. Now we'll move to the unmanned aerial vehicle, which is the second application of the flow control. So as I told you, and as you have seen during the animation, you are now aware of the working of the synthetic jet actuators. So at the bottom side, there is a diaphragm which also oscillates, and during its expulsion stroke, it generates a train of vortex structures, which help to delay the onset of stall inception. So this work was carried out at Nanyang Technological University, Singapore, and I used a particular novel kind of actuators. Here you can see this actuator comprises of 4 piezoelectric diaphragms. These 4 piezoelectric diaphragms are attached on the 4 side walls of an actuator geometry, and on the top side the O-ring is fitted. And there are such 10 actuators which are arranged in one array, as you can see here in sub figure B. So, and these actuators in an array, they are housed inside the hollow part of the wing. And I used 2 arrays. The first array was kept at 23% of the chord, and second was kept at 43% of the chord. And these actuators were open to the orifice. So on the top side of the aerofoil or wing model, we made the orifice of 5 different, one orifice consists of 5 holes of each of 1 millimeter diameter. And later I used the tomographic PIV measurements, which was the world-class PIV, tomographic PIV. I was fortunate to use that PIV technique, which cost that time around 2014. It was costing around $5 lakhs at NTU Singapore, and it consists of 4 high-speed CCD cameras which were pointing towards the laser zone. So this laser, the laser beam was issued from the laser head, and it was allowed to fall on the suction surface of the wing model, and this flow was then illuminated with the seeding particles. So we have to seed the particles with the olive oil droplets. So each droplet consists of around 1 micron or 2 micron diameter. And when these droplets pass through the laser light, these particles are illuminated, and this illuminated flow field is captured by the camera, 4 camera. And these 4 cameras were synced together so that it creates the images. And this was used to calculate the flow velocities that are passing over this, along the flow that is passing over the wing model. Now we will come to the practical implementation of the flow control techniques. We have seen that we have seen different kinds of actuators, active and passive flow control actuators, and I personally worked on some of these. The tip injectors I worked during my PhD days, and passive flow control I am working now on that. Synthetic jet actuators I have worked on unmanned aerial vehicles, but to the best of my knowledge, at the practical level, these actuators are still at laboratory level. So a lot of research is to be done. Further research is required on these actuators before their implementation. This actuator, a passive flow control device, which has been already implemented on the aircrafts, both the civilian and the military aircrafts, is the vortex generators. So when you go by a flight, and when you get the window seat, when you see just the wing, sometimes you may see that there are some triangular fins. They are fitted on the top surface of the wing surface. These are nothing but the vortex generators. The role of these vortex generators is to prevent the separation and induce some vortex structures so that the flow will not be separated and it will be energized. So these vortex generators have been already implemented, but the other actuators, they are finding, they will take some time before their implementation. And the main difficulties in their implementation or their adoption at the industry scale is their feasibility, reliability, and the effectiveness. Because when we implement something on the aircraft engines or the wing, it should be 100% reliable. There should not be some kind of unreliability, or it should work 100%. Okay. If you take example of one particular method such as air jet injection, which is an active flow control method, if we want to implement the air jet injection in real case, there are some practical limitations because of which it is not yet been adopted by the industry. And these are, when I have to inject the air in front of the rotor blade, I will need a compressed air. So either I may need a separate compressor, or I have to store the compressed air in a storage tank, and then I have to supply that compressed air. So when I say it will increase the space, already the engine is compact. So there we have to make a provision to give the space, and not only the space, there are some associated accessories along with that. And if we plan to take the help of the compressor, the function of compressor is to compress the air. So we can also bleed the air from the compressor and use that bleeded air for other applications such as the stall inception control. Okay, so that we can do. But what happens when we take the air out, the compressed air, it will reduce the compressed air mass flow rate and also the pressure rise, and it hampers the compressor operation. So it's a trade-off. Means we can get somewhere the advantage. Advantage is we will be able to control or delay the flow separation. That is the advantage. The disadvantage is we are bleeding the air from the compressor. So we are reducing the mass flow rate of that compressed air, which affects the performance. So there is a trade-off. So because of such limitations, these techniques are still at laboratory level, and further investigations are required before their adoption at the industry scale. So these are different references that I used in this presentation.
Sir, I wanted to know that vortex generators which you showed, they also suck the air back in, right?
No, they do not suck any air. They
just release the
stationary
vortex structure.
Yeah, they are the stationary devices. They do not require any power. We just have to install them.
So they continuously release the vortex structures?
Yes, when the air interact with these vortex generators, it creates the vortex structures, and in the downstream of this wing, these vortex structures interact with the boundary layer flow and keep the boundary layer flow energized.
So they need to be kept continuously on when we want to use, when the airflow is on?
Once you install, we do not have any control. We cannot remove them. I'm thankful to all members of JanyuTech for giving me an opportunity to present my work here.